Hello all, welcome to our third series in gas laws. Now so far we've learned three gas laws: Boyle's law, Charles' law, and Gay-Lussac's law. And each of these three have dealt with two specific variables and one constant each, from the variables pressure, volume, and temperature. Now we are going to move on and learn our fourth gas law and fifth one in this series today. Our fourth law that we're going to learn is actually a combination of all three laws that we just went over prior to this series. So Boyle's law, Charles' law, and Gay-Lussac's law combined together, we actually call it, it's not as difficult, but we actually just call it the combined gas law. And this combined gas law uses all three variables. Now in this case, you may ask yourself, what is our constant going to be? Well, starting from our combined gas law, we are now going to throw in the variable. Now we dealt with gas pressure, gas volume, and gas temperature. Now we're going to throw in the quantity, the amount of gas molecules that are involved. So number of gas or amount of gas, we are going to throw it in that variable that deals with the unit of moles. So the amount of gas here, we actually now get to describe this as N, the variable N, and that is in units of moles, which defines the quantity of gas molecules. All right, so in this case, we can now summarize that the fact that variables that are involved are now going to be pressure with our P, and a volume with our V, and temperature with our variable symbol T. Now, remember, if we have anything that's a constant, usually that will not be involved in the equation, because if you have a constant number of molecules that you start with, or number of moles that you start with and you end with, and they're the same, they eventually can divide themselves out. It doesn't really make much of a difference, which means the equations purely rely based on these three variables. Now, because we are dealing with three variables, this gas law, the combined gas law, actually ends up not having a graph that's correlated with it, because we are now dealing with three variables, and in that case we would actually have to go change from an XY coordinate graph into a XYZ coordinate, which is three-dimensional, and in this case, because it doesn't have a specific relationship within each variable, we can't actually predict a graph. Right? Nor does it have a relationship whether inversely or directly proportionate. So our equation now actually becomes P1V1 over T1 equals P2V2 over T2. Now you may notice that part of these equations, some of this equation is actually part of the other part of an equation, all the other three equations that we've dealt with. Like right over here, we'll notice P1V1 and P2V2. That right there is Boyle's law, right? Because you have temperature at constant. And then we end up having V1 over T1 over equaling V2 over T2 as a fraction, which shows that it is part of Charles' law. Remember when we had pressure as our constant. And then we can also see P1 over T1 equals P2 over T2, which is part of Gay-Lussac's law. So the combined gas law combines all three. That is the reason why you can observe all three of those equations actually involved in this. So you can easily remember the other three if you remember, as long as you remember the combined gas law. Now, how do we deal with problems now that we're in our fourth equation? You're going to read word problems and wonder which equation are we going to use. Well, think of all these equations that we are learning now as a puzzle. And the variables, now that we have four variables, we have P, V, and T, and N. These are like puzzle pieces, which means you have to find the puzzle that fits exactly these specific puzzle pieces for that entire question. And they are very specific, so only one equation can fit for a specific condition. So let's look at an example over here. A cylinder with a movable piston that has an initial volume of 3.65 liters is carried up a mountain. The pressure at the bottom of the mountain is 755 millimeter mercury, and the temperature is 29 degrees Celsius. The pressure at the top of the mountain is 687 millimeter mercury, and the temperature is 291 Kelvin. What is the volume of the cylinder at the top of the mountain? Right here, you may have already guessed the question. It's a condition starting from the beginning. Our initial is at the bottom of the mountain, and we're eventually climbing up the top of the mountain, and we measured the condition, and we are trying to predict or calculate what that volume is at that top. So at the bottom of the mountain, all conditions will be our initial. So step number one in identifying these word problems is go through the numbers and the units associated with it. So within this question, we notice 3.65 liters, 755 millimeter mercury, 29 degrees Celsius, 687 millimeter mercury, and 291 Kelvin. After we've gone through and analyzed all the numbers, we then ask ourselves, what did the question want us to find? And with any luck of we being able to read English, we can analyze that. It's asking for what is the volume of the cylinder at the top. All right, so now we can easily identify each of these units associated with the number value on what variable they are associated with. So right here, our 3.65 liter. Unit liter means it is associated with volume. Since it's the bottom of the mountain, that's my V1. We have our 755 millimeter mercury. That's a unit that's always associated with pressure. So we can assume that this is easily our pressure. And our Celsius temperature is going to be our T1. Now remember, when we're dealing with temperature, it's currently in Celsius, which means we want it converted into Kelvin. And by how do we do that? Is by adding 273. So we would add 29 degrees Celsius with 273. And this will give us 302 Kelvin. Oops, that should be 2. All right, let's keep on analyzing and identifying these. Millimeter mercury, again, that's a unit for pressure. So we put P2. And then we have 291 Kelvin. That's already in Kelvin, so we don't have to bother with the conversion, and that's our T2. And finally, what is our volume? That's our volume, final volume, so V2. Note that the only variables involved within this question is volume, temperature, and pressure. 3 variables. So far, out of our 4 equations, there's only one equation that deals with 3 variables involved directly, and that's our combined gas law. So we can just easily plug those values right into this equation. And all we need to do is solve for our V2. It's just basic algebra now. You know, are solving for V2 as our unknown. So if you put that into your calculator and cross multiply or do whatever, multiply by the reciprocal, and you will end up with volume as 3.865 liters. And technically, according to sig figs, you should only have 2, so technically it should only be 3.9 liters, but our answer is being generous. All right, so let's move on into our 5th law. Now that we've gone through combined gas law and been introduced to our 4th variable, our 5th gas law actually deals with our 4th variable. So our next law is called Avogadros' law. You may already be familiar with Avogadros, the name Avogadro, because the unit before this we went over in stoichiometry. We dealt with Avogadro's number, which means Avogadro's number is 6.022 times 10 to the power of 23 atoms or molecules, particles that are in a single mole of a unit. So we're now dealing with quantity because Avogadro's number deals with the number of molecules in a mole. So Avogadro's law, we are now going to be dealing with a variable that is directly affected by number of molecules. If you think about number of molecules, if you're adding gas molecules into a container or a space, what is going to change immediately? Well, the volume for first. Volume is directly affected, and that is what this equation is going to be about, or the law. So at a constant temperature and pressure, note that we now are dealing with 2 constants. We have T and P. So an easy way to remember is Avogadro is all about its Tp, being constant. Now, what's being involved? Avogadro, assuming that it's dealing with numbers, is dealing with the amount of gas in a sample with volume. And note that the wording here, statement, If the number of gas increases, the volume increases. Now, hopefully this statement makes perfect sense to you, because if you think about it, it's like a balloon. If you blow air into a balloon, you're adding gas molecules into that balloon. And what's happening to that volume is that it is increasing in volume as you add number of gas and more gas molecules in there. And vice versa. If you let gas molecules out of the balloon, you end up with a slightly more deflated balloon. So we can say that the volume of the gas and the amount of gas are directly proportionate. When one goes up, the other goes up. So we have volume V, and then we have the amount of gas in moles as our variable N. And we can now put this in an equation saying that this is V1 over N1 equals V2 equals N2. Note that directly proportionate shows that the equations end up in fractions. Now, the statement directly proportionate also should give you an idea that and be able to help us predict that a graph exists. So far, all the directly proportionate relationship gas laws all have had the same graph, and it has been a straight linear line. The only difference is the fact that the variables that are dealt with it are the ones that are in the equation. All right, so keep that in mind. Even though we have same graphs there, you just have to keep an eye out for those axis values. All right, so this is a short diagram here that kind of shows you that if you increase the volume of the gas, naturally we're talking about more gases being added on. And note that the temperature, the pressure is staying constant, and the temperature should be staying at constant. All right, so let's look at a word problem here, and we can wrap this up. Again, all about these word problems, it is so simple. All you need to do is first analyze a number. So a 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? Assume constant temperature and pressure. Now, some questions will actually give you that assume portion, which gives you the condition, and actually this one specifically already gives you what equations to use. But let's analyze as we've been doing. 4.8 liter, we have 0.22 moles and 6.4 liters. And then we read and ask ourselves, what is the question wanting us to find? This specific one, how many additional moles? So note that this question is asking something a little bit different and conventional, but we'll deal with that in a bit. So let's analyze these. This is the starting volume, so that's my V1. And number of moles, we're dealing with numbers, so N1. Alright, and then we have 6.4 liters, so that's my V2, and number of moles is what we're trying to figure out. Note that the only variables involved are volume and numbers, and there's only one equation that fits, which means that we can now plug this into our equation. Alright, so this is going to be plugged into our Avogadros law equation, and then we can now solve for our unknown N2. Alright, when we do so, we will end up with 0.29 as our final amount. However, the question asked, how many additional moles of helium gas must be added to the sample? Well, considering that this is my starting and it ended up being 0.29, how many was added to become 0.29? All we need to do is subtract the difference. So 0.29 moles, and you subtract it by 0.22 moles. And we get 0.07 moles that was additionally added. Hopefully this helped with everybody. This summarizes all our 5 gas laws. Thank you, and I'll see you for our 6th law in our next one or in our series.